In this video, we begin coverage of x86 Intel 32-bit platform assembly programming language, and we'll be using Microsoft Macro Assembler to translate our assembly programs into machine code. This is the presentation that I'm opening for this section. So when we speak about high-level programming languages such as C or C++ or Java, they're generally very portable. All you need to do is just to be able to find the appropriate compiler on the platform that you would like to use, and there will be just perhaps no modifications or very few modifications to the existing source code. You're expecting this to move from one platform to another without much problem. So high-level instructions such as if and else statements and other constructs, loops, operators, data types, all of these building blocks that you use to program in high-level languages make program development fast and straightforward. Just a few lines of code can give you a lot of results. And program maintenance, therefore, is also benefiting from using high-level programming language. So compiler of a high-level programming language translates the source code to the target machine language, or in case of Java, it translates it to a Java bytecode, which requires Java virtual machine environment to execute. So why then we're still interested in assembly programming? Some drawbacks for programming in assembly is that programs are not portable. You would have to rewrite the entire program in order to move it from one type of machine to another. Learning it is a little difficult. Programming in assembly is very tedious. So you have to worry about bits and bytes and the sizes of data type by explicitly describing them in every situation. So you're not benefiting from data type safety of high-level programming languages. So high-level programming languages should be natural preference for all common application types. However, at the same time, assembly gives us direct and complete control over the system hardware. So the set of instructions that you write is going to be exactly the set of instructions which will be executed by the CPU. This is your decision of exactly how to control the hardware directly. So this becomes paramount importance for writing device drivers, which are part of the operating system. If you want to design or contribute to the design of an operating system, again, you will end up perhaps using existing assembly source files or writing your own. And of course, in embedded systems programming, it's still pretty popular platform to program instrumentation devices that you would find, for example, in the cockpit of an aircraft. So sometimes writing inline assembly, mixing assembly language instructions in C and C++, sort of like hybrid programming, is also allows you to be able to take advantage of a few tricks that could be specific to a certain platform and the application that you're designing. So this is, of course, important points, and they require your knowledge of assembly. There are areas where the speed is everything. For example, internet data encryption, aircraft navigational systems, medical hardware control. So this is where if you understand the principles of the hardware that you're working on, and you know how to create the code that runs faster on those platforms, your choice could be assembly program. Also, of course, assembly program could use so few resources that it will be very difficult to compete in a high programming language with the assembly version, and therefore you can fit more into less space. And in debugging the code, sometimes trying to understand the reasons why program has crashed or misbehaved in some other way, you'd have to be able to understand the disassembly, or in other words, reverse engineer existing code to investigate the cause of some serious problems in the original application. Sometimes disassembly could be looked and be used to find bottlenecks that would allow to optimize the code. And of course, you're still learning how the hardware works. So these are some highlights that I wanted to give you regarding the importance of assembly and your knowledge about the assembly language and what the environment looks like and how you could write your own code more or less comfortably in assembly. So we're going to use Microsoft Macro Assembler, which is a long-standing type of assembly from Microsoft, and it's quite reliable, well documented, and relatively easy to get started with. So we've looked at hardware level design of circuits using various logic gates to build devices such as 4-bit adder, and then later we added detection of overflow of the result to that device. And we also looked at the comparator device that could compare magnitudes of 4-bit numbers. So all of this is based on transistor wiring and is still very much hardware level. What is machine language? Of course, it's the language of unique codes of zeros and ones, encodings of CPU instructions. But what's even more important is that how concepts such as if-else statements in high-level programming language are realized at the machine level. What exactly happens when you say if condition and then begin to write what would you like to add to your if block statement. Also, how does your executable program interact with an operating system? So a lot of details at that level could be unveiled by looking at the assembly level or machine language level implementation of software. And of course, many more fundamental questions could be answered by looking at how a particular model of computer works, but how we look at it is that we want to be able to discover what are the sets of CPU instructions that provide all of this functionality. There's some links to resources on the web, and there's some books right here. And in the rest of this course, when we're talking about machine language programming, the focus of our attention is going to be on using CPU registers, which are temporary data locations directly inside the CPU, like named memory cells directly inside the CPU. We will also look at how these CPU instructions that we will learn about can address and access memory and different data types in computer memory. Of course, from day one, we started talking about representations of data. What are signed numbers, unsigned numbers, 2's complement numbers, other types of encodings. So both numeric formats of data stored in computer memory and character strings. Of course, I already mentioned 2's complement integers and what impact does it make in programming in assembly. Also, there are instructions operating on individual bits, instructions to handle string of characters. Obviously, there is support for text data on part of the CPU. It's not just arithmetics. Of course, to implement logical decisions, we need to be able to loop and branch based on conditions. Like if condition, we need to be able to jump to a particular part of the program. And finally, we'll be looking at the organization of procedures, so that the main function or main procedure in our application can start making calls and expect these calls from other procedures to return. So this is yet another part of our coverage that we're going to discuss: ways to transfer control, how do you pass parameters to functions, and what the local variables look like in computer memory when we code procedures, because upon return from a procedure, local variables will be deleted. So these are topics specific to procedure coding.